name's Elizabeth Sherry, and I worked on the optimization of monomer ratios in the adhesive and preparation of electrospun adhesive support for layered structured smart adhesive. So the project that I worked on could be broken down into 3 phases. The first phase being the electrospinning of pan, the functionalization of pan, and the IR study of functionalized pan, and then the treatment of the functionalized pan. And then phase 2 would be the synthesis of the polymer, which contains the adhesive. And then next would be JKR testing, which is to test the adhesion of the polymer previously created. And then the last phase, phase 3, which is for future work for Dr. Manuel to conduct, and that is the incorporation of boronic acid. And this is what's going to essentially provide the adhesion with smart properties. And he will then assemble the 3 layers. So the reasoning behind electrospinning is because electrospinning provides, first it provides ease of functionalization, which we then use later on, but most importantly, it has a high surface area to volume ratio. So this is really important in this project, but also to the real world, because in the real world, for example, the pharmaceutical industry, a nanofibrous membrane will provide faster drug dissolution. And going back to my project, nanofibrous membrane is really important because of the ease of functionalization. So the next step after electrospinning pan is to functionalize it. The reason why we're functionalizing it is because we want to improve functionality. We want to implement an additional functional group, and that functional group is a carbonyl, more specifically in primary amide group. So after we functionalized it, we want to confirm that the functionalization was successful. So we did that by running a IR spectrometer. And essentially what that does is there's going to be infrared radiation transmitting and producing frequencies, and this will be recorded onto a spectroscopy graph. And on that graph, there will be peaks that are broad or sharp or weak. And specifically, we were looking for a sharp peak at 1690, and that is what we got. And this is indicative of a primary amide group being present. So with the IR spectroscopy, we were able to confirm that the functionalization was successful and the primary amide was produced. So after we functionalized polyacrylnitrile, which is known as PAN, it is now known as polyacrylamide because of the amide functional group. So going forward, we'll be referring to PAN as PAM with an M. And after we had concluded the functionalization of PAN, we needed to treat PAM with Nafion. And the reason why we were going to be treating it with Nafion is because Nafion is a sulfonated polymer and it has conductive properties. And these conductive properties is going to allow the production of a cation permeable membrane. And once that's done, we have completed one of the layers for the multi-layered membrane, and then move on to the next step, which is to synthesize the polymer that contains the adhesives. So this is going to be an additional layer, and this layer has the adhesives. But before we can begin synthesizing and casting the polymer onto the membrane, we must first identify which ratio of DJA to DMA is going to give us the maximum adhesiveness. So Dr. Manuel and I synthesized 4 batches actually of the adhesive DJA and DMA. Initially, we had synthesized 3, but we stumbled upon an obstacle, and that was that one of the ratios had a very, very, very low yield, almost to no reaction. So we had to disregard that and add an additional ratio, and that is 75 to 25. So the ratios we had worked with, again, is 75 to 25, and then 80 to 20, and then 70 to 30. So we had synthesized this by using a round bottom flask, and we put all of the adhesives, so the DMA and the DJA, and we also had put the radical initiator as well as the solvent, and we purged it with nitrogen to remove any oxygen, because if we had kept oxygen inside the round bottom flask, this would oxidize catechol, and then catechol will no longer have its adhesive effectiveness. We then used a centrifuging technique to washed the round bottom flask with diethyl ether, and the centrifuging technique is what allowed us to have the precipitate form at the bottom. And then once that was done, we went to remove the excess diethyl ether, and then we placed our sample to be dried in a vacuum. And we are doing this because we want to also eliminate the solvent, but also because any excessive heating will cause our polymer precipitate to continue reacting, and we didn't want that. So after that was completed, we had our polymer that was fully formed, and next we needed to test the adhesion. We needed to test how well this polymer could be sticky. So we performed the JKR, which is known as the Johnson-Kendall-Roberts contact mechanism of adhesion. And the purpose of this is we wanted to model and represent the force that is required to release the indenture from the adhesive. And from doing this, I was able to infer that, well, before I say that, I want to say we did this about 9 times. So we had 3 batches, we had 80 to 20, 70 to 30, and 75 to 25. And with each of those, we had tested it dried, washed, and with a buffer of pH 3 of 3.0. So we did this 9 times. And after that, I was able to infer that having catechol and acid promotes stronger adhesion. So once we had conducted the JKR analysis, we then needed to run a MATLAB code that will allow us to produce a graph to visualize what we were working on. So in figure 4, we can see that there's a comparison of the strength of adhesion. So once I have the MATLAB code, I worked with the force that it produced and the surface area that it produced to calculate the strength of adhesion. And in this figure 4, we can see that the ratio 75 to 25 had the greatest amounts of strength of adhesion. So to conclude, we can confidently say that the ratio 75 to 25 provided the maximum adhesiveness. So into phase 3, this is the portion of the project where we will be incorporating boronic acid, and this will promote the smart adhesion properties. This is for Dr. Manuel to do, but going forward, this will be a 3-layered membrane, and this can be used for painless wound dressings, as well as reversible adhesives for assembling prosthetics. And I would like to acknowledge the support from the NSF Award and mentorship from the Keweenaw Bay Indian community. And lastly, I would like to reflect on my experience being a part of the REU program, as well as having experiences with the KBIC, the Keweenaw Bay Indian community. One of my most memorable events would have to be the water walk, because I felt like we were all a part of a team. And like, although some of us couldn't walk the entire 13 miles, it was really reassuring and just really wholesome to see individuals were volunteering their cars as shuttles to shuttle anyone who needed a break or who needed water. And then later seeing them at the powwow, I really felt like I was a part of a community, and the KBIC really is a strong community that looks out for each other and cares for each other. And I want to say thank you to them for educating me and sharing their experiences with me. And thank you for listening. Goodbye.